Eh, Tenemos el día de hoy al doctor Apurba. El doctor Apurba trabaja actualmente en el departamento de recubrimientos funcionales y alta temperatura en el Centro Alemán Aeroespacial en Colonia, con proyectos financiados por la Administración Espacial de Alemania para manufacturar y probar supercapacitores para aplicaciones en satélites. Bueno, tiene varios proyectos financiados por la Unión Europea, principalmente dirigidos al desarrollo de dispositivos de almacenamiento de energía electroquímica, como baterías de ion litio y supercapacitores. El doctor Apurva fue de los estudiantes, del 1% de mejores estudiantes de la India también. Y bueno, también ha publicado 44 artículos de investigación y 3 capítulos de libro, y es editor en varias revistas internacionales. Doctora Apurva, again, we are very pleased to have you. You have 25 minutes for your presentation, and then we have a short time for questions of the public. Thank you very much. Welcome to our conference.
Okay, thank you. First of all, thank you for your invitation and a nice introduction. So I'm very happy to present my work, some overview of your current research. So today the title of my presentation is Advancement in Supercapacitor for Future Aerospace Application. Okay, first of all, can you see my screen now?
Yes, we can.
Okay.
Yes, I can see your presentation.
Okay, and you can hear me clearly, yeah? Can you hear me?
Yeah, yes.
Oh,
yes, you can hear me. Yes.
Okay, thank you for this thing. So I'm Dr. Apurba, working as a research scientist at German Aerospace Center, Cologne, and this is some new name of our institute. So I'll give some more things. In the beginning of my presentation, I would like to give some short overview about the German Aerospace Center. So German DLR is a German name, Deutsches Zentrum für Luft- und Raumfahrt. In English is German Aerospace Center. Is the German government of German research center focused on the aeronautics, space, energy, transport, security, defense, and digitalizations. So DLR has 54 institutes at different. Disappoint. Okay. 54 institute in different locations. That means 30 locations in all over Germany. So approximately 10,000 employees, including the scientists, senior scientists, a lot of PhD students, researchers are working in the DLR. And the main headquarters of this DLR is in Cologne, where is our institute, the Institute for Frontier Materials on Earth and Space. It is very new name of our new institute. Beforehand, it was the Institute of Material Research, and recently, in the next month, in 2nd of December, it is going to be officially published the new name of institute. And another things, the most important, the last year in our institute or in our DLR, we launch a new research facilities that's to investigate the atmosphere or soil of moon in Earth. So its name is Luna, so moon on Earth things. Lot of ongoing research is going on in these things, and not only in Germany. The DLR has different offices and center outside Germany in Brussels, Paris, Tokyo, and Washington DC. So if you would like to know more information, you can visit the website of DLR and you will get more information. You are all welcome to visit our website. So these are some ongoing project, energy related project is going on in my group and department. So mostly on supercapacitor and batteries things. The first one is the decentralized power supply electric propulsion deep. It is mostly funded by DLR internal project program directory PACE. project. And another two project is European Union funded project Phoenix. This Phoenix project is focused on the lithium batteries, that is mainly on the self-healing functionalities to detect the degradation and repair the damage via advanced battery management systems. And another project also on the supercapacitor, it is called Graphene. That is also UA funded project, and also it's a graphene based flexible and structure energy harvesting and storage devices. And these are the some outlines that I'm going to present in my talk in these things. So I'll not go per point by point. I will go to the slide. You can see one by one. So first of all, the main topic of this presentation is energy storage. So when we ask what is energy storage or what we know about the energy storage, first name comes in our mind is the batteries, because we all have the electronic gadgets, laptop, mobile phones, and other portable, the watch, smart watch, and a lot of things. Yes. So batteries for giving this energy. So batteries means we know the lithium and batteries. First, the name comes in our mind. Also, lithium batteries. The main this properties of lithium batteries is charge discharge mechanism. The charge discharge mechanism is intercalation deintercalation of the ions. That means the ions can go through intercalate into the electron material and also come out from the electron material. So that is the main reason the lithium ion batteries, so battery takes longer time to fully charge, and it can also discharge for a long time because it needs long time to intercalate and deintercalate the ions from the electrode materials. So it charging time is very high, few minutes to hours. Energy density is around 250 watt hour per kilogram, and power density 300 watt per kilogram. Cycle life, this is 1500 cycle. That you can imagine in the real life. That is whatever you have the mobile phone in your hand at the moment, after 3 years or 4 years you cannot expect that your batteries run to longer times. So that's been 3 years, 4 years, or maximum 5 years. So if you charge your batteries or mobile phone every day, that's mean you can imagine or calculate this is the cycle number. Cycle means full charge, one time full charge and full discharge. This is one cycle. And cell voltage for the lithium batteries works 3.6 volt to 3.7 volt, and operating temperature lithium batteries can work in the minus 20 to 60. Another things, the capacitor. This is dielectric capacitor that we also use on a lot of electronic devices. It stored the charge electrostatically, and it can charge very quickly, the same milli to microsecond, but its energy density is very lower, so in the range of 0.1 watt hour per kilogram, but it gives high power. So high power things. So the 10 kilowatt per kilogram kg. And the life cycle is very high, even few years it can work, and it can also work in the high voltage, and operating temperature is quite high. But if you need in the current generation, whatever we're using the devices or something, we need some higher energy density as well as power density. So you cannot imagine to use the capacitor battery. So we are first of all, our idea was used to develop such a device with the combination of battery and capacitor that can fulfill our requirement. But it it makes other problem, cost problem, and also the weight problem, and some safety issues. After that, there's some research going on the supercapacitor. That is the bridge, makes the bridge between the battery and capacitor. It can charge in the two process, electric double layer process, electrostatic way, and also the redox reaction, oxidation chemical reactions. It can charge in the millisecond to second, quite faster than batteries, and almost in the range of capacitor, not in the dielectric capacitor, but it gives higher energy density compared to the capacitor, and higher power density compared to the batteries things. So it can give some high power density values. A cycle life relative to the battery is quite higher, so 100,000 cycles, and voltage is up to 2.3 to 2.75 volt. And the also the uh, mm, temperature, operating temperature is relatively higher. compared to the batteries and capacitor things. So these are the basics types of electrochemical energy storage devices. And the future. So as we already mentioned, this is a plot of Aragon plot, that is means of plot of power density versus energy density. So you can, from the previous slide, you can imagine the capacitor, that's mean dielectric capacitor, can give us high power density but very low energy density. On the other hand, the batteries for lithium and batteries or other type of batteries, it can give high energy density but very low power density, and also the fuels in the same range. But still now, the electrochemical capacitor, that's called supercapacitor, it bridge the gap between the capacitor and batteries. But our expectation is going rapidly day by day. So what is the future things? We are trying to develop some batteries, a future device that can provide us a high power density as well as high energy density, so that we are trying to reach in this point, in this range, in the Aragon plot. That means the possibility is in two ways. You can improve the performance of electrochemical capacitor, supercapacitor, or you can develop a new type of batteries of fuel cells that can improve the both power density and energy density. So our demand is high capacitance, moderate energy density would be also good, and high power density, highly stable, because we are also suffering from a lot of safety issues from the lithium batteries, other things. So stable, lightweight. Weight is very important because we are all are very fascinated to use some such device should be very lightweight. So it can easily be portable, that's it, and safe and cost effective. So in to fulfill this all these requirement, so current research focus on supercapacitor or new type of batteries. Maybe it's a post lithium batteries, other type of pure batteries. So people are looking forward to build or develop a new type of future device that can fulfill our requirement. Next is the history of supercapacitor. It the first supercapacitor or capacitor things is developed or launched in the 1745. You can imagine after almost over 100 years, it's the first concept on the double layer capacitor. But again, it stopped, and after the almost 100 years is the first patent on the inverse electrochemical capacitor device. In 1979, that's the, and after 1990, you can expect this. So the focus, research focus on electrochemical energy storage, the supercapacitor is slowly increasing. But I would say that's after 2000s or even 2005, this research on the supercapacitors become very popular, and this is a major research, hot topic of the current research of, due to their many advantages over current market leading lithium ion batteries. So the main motivation is, you can easily imagine that nowadays we are using, everybody is using in our daily life, even as household, a lot of portable electronics things, and the demand of requirement of portable, flexible daily use electronics is increasing. So that's needs some smart devices that's to fulfill the energy requirement, because nowadays the demand of low carbon emission energy is also increasing so rapidly that there is an urgent need of advanced energy storage device that can fulfill the future requirement. So not only that direction, with this trend of this decarbonized energy, the future future aerospace and aircraft system also looking for some high power storage and lightweight, cost effective energy storage device that can be operated in the challenging environment, and that can power the spacecraft and when they are in the dark side of the raceway, and to using the solar energy or something. But supercapacitor in this case very promising in the last decade. I could say that they're very promising for the and many aspect aircraft landing gear system, because supercapacitor it can gives power high power at a short time. If you need to break a system or if you need to start an engine, you need a high power, some thrust. That is not possible most of the cases for battery, or you need to use a huge battery pack. But for the supercapacity, it can give easily a thrust, a high power in a certain time, is very small time. So that, and also it is very safe. So that's why the people are interested in the supercapacitor research. And it can be operated in the extreme temperature, and the lifetime is quite high, far away from the batteries things. So it has capability to rapid power generation and storage. And not only that, the other things we can fulfill the future decarbonization directions. So this is the main reason that supercapacitor also giving the lot of advantages in the future or future aerospace aircraft situation for small satellite and others monitoring and controlling the aircraft systems. So the main role of supercapacitor in aerospace application, that if you know or heard of these things, the lot of things, the geostationary Earth orbit surface, that it can prevent, supercapacitor can prevent a satellite power supply from the fluctuation during this change of the load. So it can start of the electric propulsion, thrust, orbit change, any kind of change or load change of the satellite, it makes some fluctuation of the supply, but supercapacitor can prevent this kind of fluctuation. And other things, synthetic approach radar systems. So imaging devices are characterized by the emission of narrow high power pulse stream. So that I mentioned, the supercapacitor can provide high energy required for a very short time. So it is very capable for the supercapacitor over batteries things. High power radar supply, small satellite, also small satellite, the main problem or main research on this aerospace things to reduce the overall weight of the satellite. So still the battery pack, we need to use the battery pack for to fulfill the energy requirement, but battery pack it itself take a pace and it increase the weight. So people are trying to reduce the weight, overall weight of the satellite using the supercapacitor, because supercapacitor is very lightweight and also it is very safe. It doesn't have any other problem for safety issues. And flight control and monitoring of the systems, this aviation system, aircraft systems, is very easy to control with the supercapacitor, because it can give high power and also the energy according to the requirement. Hybrid energy system, so where the supercapacitor or battery not only itself is sufficient, then the current the aerospace research also, they are trying to combine this supercapacitor and lithium batteries or different batteries to make a hybrid energy pack, energy bank that can fulfill when we need high power density or high power, the supercapacitor can work, and also where we need the high energy, lithium batteries can work. But overall, the weight of the energy pack can be reduced even up to 50 to 70%. And the electric propulsion, this thruster to replace the cooled gas things, and supercapacitor managed to improve the specific impulse up to 28 to 30%. This is the current report things on research on the supercapacitor for aerospace application. So not only that, in the current stage, the future of supercapacitor in the aerospace application, that it is expected that supercapacitor will replace the batteries things, because it can be integrated easily on the structure in the aerospace aircraft, and it can work as a intelligent energy storage systems, and they can provide short high current power suitable for several applications such as electric vehicles, recovery of braking energy in vehicles like buses and train, etc. And in the military cases and aerospace cases, their quick power delivery, low temperature operation, and long life make them very ideal. But there is also some challenges, because the most challenges for supercapacitor is lower energy density. Up to now is practical real device case is in the range of 10 to 15 watt hour per kilogram things, and lower voltage compared to the battery things. This can work below 3 volt. This still now that, but for real devices, I would not say or talking about any material or any small devices in the laboratory scale. And higher self discharges every day, 10 to 15% to 20% self discharge rate. So this is the most things that we have to overcome this point. So the main component, the device, the main component is 2 electrode, 1 separator, and this middle, and also the electrolyte, this thing. So anode, cathode, and separator, this is the main component. So most of the cases, the still now the different types of carbon based material, activated carbon, carbon aerosol, graphene are using for electrode material, electrolyte, different types of aqueous electrolyte, ionic liquid, polymer electrolyte using, and current collector for anode, cathode, the um, copper, aluminium, current collector use of substrate for the electrode preparation, and also the binder. Binder also makes very strong influence on the device performance. So still a PVDF, this is same systems of using, and also the separator. Separator, different types of separator, the ceramic separator, glass fiber separator, polymer, paper separator, different types of separators using in the device. Charge storage process supercapacitor, according to the materials things, there in the carbon based material, there's charge stored in the electrostatic way. That means in the interface of the electrode interface, you can imagine from this here, the ions can store in the pores of the electron material or the surface. So there is no change of electron or redox reaction, nothing, no chemical reaction occurs in the electric double layer things. For the redox type or pseudocapacitor electron material, there is some redox reactions occurs at the interface of electrode electrolyte, and there's exchange of electrons things. And mainly metal oxide conductive polymer used for the this pseudocapacitor material, and hybrid things. Nowadays, people are making some composite things with the combination of carbon-based material and metal oxide, different types of polymer things, to get the advantage of both electric double layer and redox active pseudocapacitor. And based on the device fabrication, there is some 2 types of symmetric supercapacitor. That means the 2 electrode are the same. Anode and cathode material are the same material. So then it works as a symmetric. So it could be carbon based material, it could be some metal oxide based or polymer based. But if the both electrode are same material, then it's called symmetric. And asymmetric supercapacitor, it's a asymmetric. That means the electrode are different. One could be carbon-based material, other could be some redox active material, or could be composite material, or the 2 electrodes should be different. If this is the 2 electrodes are different material, so then it's called asymmetric supercapacitor. Symmetric supercapacitor can give lower energy density but higher long cycle stability. But asymmetric supercapacitor can give high capacitance value, high energy density, high power density, but sometimes it gives very unstable or not so long cycle stability values. So cyclic voltammetry, there's the main characterization curve. There's electric double layer capacitor. It looks like the current voltage relationship looks like almost rectangular shape. Things. And pseudocapacitor, you can look from the deviation of this rectangular shape. This is type of pseudocapacitive electrode material. If you get this kind of nature, so it is a type of battery type material, electrode material. So from this curved nature, you can also imagine, or you can identify the material properties for the charge storage mechanism. And from these things, you can also calculate the capacitance value. The capacitance of the charge stored covered by this area, closed area. And using the equation, you can clearly calculate the capacitance values. These are some basic equation. I think if you're working on this kind of the materials or research, then you can know this charge. The capacitance things is proportional to the current, discharge current, and also the discharge time things. And the energy things, the most important things is the energy density. Energy density, in the 2 ways you can improve or increase the energy. One way, you can improve the or increase the capacitance of the material, or another way you can increase the voltage of the device. That means voltage is mainly depends on the electrolyte that you are using. So because voltage is, energy density is proportional to the square of the voltage. So sometimes people are most interested on the use of different types of high voltage electrolyte things to improve the energy density, and also the according to this power density, this one. Some materials, so if you know this, the for the charge storage things, the porous material is very superior for the supercapacitor things. There is some values. There's micropores, which is in the 2 nanometer range diameter, so it is ion cannot infiltrate. Mesopores, the pores diameter between 2 to 50 nanometer range. That means ions can easily infiltrate through these pore structures. And macropores, the larger than 50 nanometer in diameter. That means ion only accumulate on the surface. It cannot infiltrate through these pores things. And up to now, from this, the most of the cases, the what type of material, the carbon aerosol that you can from different color, you can do these things, carbon nanotube, but the activated carbon still now, I would say still now, the commercial supercapacitor electrode material is based on the activated carbon. And, other carbon based material is still going on the research to improve their performance, but most of the cases the activated carbon gives the best result up to now for the commercial application. And selection for the material, if you work on the development of materials, so once you develop a new material, you first you check the cyclic voltammetric curve, and from this peak position you can calculate or explain your material properties. So the first is peak current. This is called peak current, is from the power law. This peak current is the contribution of the capacitive current and diffusion current, or redox current. So it's some the general equation A, or the scan rate to the B, and if you some general expression, if you plot this curve according to your values, so log peak current to sweep current, then you will get the slope value of B, and this B value gives you the information about your material. If the B value is exactly 0.5, then the material diffusion control behavior, that is the redox reaction is occurs. This gives a high energy density but low power density and low cycle life. But if you get the B value is a 1, this 1 is the ideal one, and 0.5 is all ideal for the batteries thing. So capacitive behavior for 1. So this capacitive behavior, low energy density but high power density and high cycle life. So you can see this is capacitive precision zone and this is diffusion control zone. But nowadays the current research on the material, electromaterial, is to develop some material in this range. That means it gives uh, both contribution, capacitive contribution and redox reactive contribution. So our new material, the B value should be in the range of 0.5 to 1 values. This is the transitional area. The new material, whatever you look the papers or research on the all are trying to get a new material in the composition to get the B value in this range. So to get the both contribution, capacitive contribution and redox active contribution. And from this other same expression, if you extend this equation after getting this A value and this thing, this is the other equation. This is for capacitive and this is for redox active things. So, and after this, if you plot some data from your CV curve, so this by what's this one, then if you get a slope values from this K1 and K2 values, this is the general expression you will get in the different literature and also from some research paper. And from this K and K2 values, you can get all this parameter of your material, and this gives you the details information about the materials. So if this K2 is greater than K1 value, therefore pseudocapacitive material is contributing mostly over double your capacitive behavior. And electrolyte, you know, some very common electrolyte, aqueous electrolyte, organic electrolyte. So every electrolyte has some advantages, also some limitation. The mostly aqueous electrolyte and organic electrolyte, they have the this aqueous electrolyte is a low voltage window, so that means it probably gives you low energy density. So it gives high capacitance value because the movement of ion is very fast, and this gives um, high amount of energy, ion dense things. And other type of liquid, ionic liquid things, this kind of this gives a relatively higher voltage, and also this cost effective, and also the stable, mostly the stable, because current research for aerospace application, supercapacitor, we are not looking for to improve only the capacitance values or energy values, because simultaneously we have to look for the how long it can work, how the stability of their performance, and not we're looking for some 1,000 cycles or 200 or 5,000 cycles. Not, we're always looking for the 1 million cycles or over that, and how the performance is stable over the 1 million cycles. So that's why the current research is also focused on the polymer matrix based electrolyte. So different types of gel polymer electrolyte, solid polymer electrolyte, and also the to combine with the high voltage ionic liquids. So ionic liquids, it has a lot of advantages: good thermal stability, ionic rotor, and good chemical stability, eco-friendly, low melting point, and non toxic. Depends on the composition of the ionic liquids also. And the if you combine these things with the and this conductivity, this liquid ionic liquid based on pure ionic liquid based electrolyte, this is very high conductivity, risks of leakage, because leakage problem is also the major problem for lot of practical application or even in the space application. So leakage problem, and mechanical stability is poor, and packaging issue, because at the end of the day we have to integrate our supercapacitor device in the structure of the aerospace, that is satellite, whatever this aircraft system, everything. So if it is there is some leakage problem or the packaging issue, then it cannot be used. So I liquid based gel polymer electrolyte, it gives high conductivity, and risk of leakage is low, and mechanical stability is medium, and packaging is easy. And people are also moving forward to the solid polymer electrolyte, because mechanicals are very good, and packaging is easy, and there is no leakage problem. These are the current thing. So there's some our almost recent work that is also published in the last year. You can also check this paper, and you will get some more details about the papers and work. So from this CV cyclic voltammetric curve, you can look that for only for this paperwork or research, that time we measure up to 2.8 volt, and all the CV curves gives the same performance. Also GCD curve, and also this is gives high capacitance, total capacitance in the about the 5 Fed. And what is the electrode material? We use the commercial electrode material, activated carbon based commercial electrode material, and we prepare in our laboratory scale 5 by 5 centimeter size, this thin pouch cell, and it gives by 5 by 5 centimeter size cell, it gives almost 5.8 farad, and energy density 10.9 watt hour per kilogram. And not only that, this cell works. I measured this cell personally, and in our laboratory, it works over 165,000 cycles, even at a high current, 1 ampere current. So I not show this result, only this. You will get more information if you visit or read this paper. And if you have any more question, you can also contact me anytime for the details information. And future, the supercapacitor market. So after I would say this 2010 or 2015 supercapacitor market is going and the high there. So supercapacitor from the 2021 to 30 almost is very high and is increasing rapidly. So it is expected that global supercapacitor market size is to very high to $5 billion to 25 things. So lot of research is ongoing on the supercapacitor, and many aspect, many section to use of the supercapacitor. So conclusion, I would give you some sort, if I'm not over the time. So aerospace industry is witnessing the significant transformation in the energy storage and power supply. Supercapacitor is really playing a good role, key role in the evolution of this energy store. And for the electron material, I would say the porous material. Porous electron material enhance the energy storage performance. And for the electrolyte, whatever the solid, gel, different types of polymer electrolyte, infiltration of the electrolyte into the pores of the electrode material, improve the long cycle stability. And not only that, I would say the most important thing is whatever you have, the best part from electrolyte, electromaterial, but if your packaging, your assembling of the device is not so good, then you will not get your expected result. So integration or encapsulation of the device is very important things. And supercapacitor will continue to redefine the efficiency and capacity in the future. So it is the use future of the supercapacitor in many directions. So these are the special issue I am now dealing with this thing. So you are all are welcome to visit this special issue things. You can also scan this QR code if you have any research would like to submit. So I'm also one of the editor of this special issue. You can also visit anytime and also submit your research, and you can also share this information to your colleague if they are interested to submit this paper in the special issue. And thank you all of you. I would also like to thank the DLR, the PACE Directory of the German Aerospace Center and European Union for to the financial support to continue our research. And these are my contact details. You can anytime contact me if you have any question, any other things, other information if you need. So you are welcome to contact me, and thank you for your kind attention, and also looking forward to have some questions and more discussion. Thank you.
Jimenez-Melero es, es Joint Chair de la Autoridad Británica para la Energía Atómica, en materiales para fusión nuclear en la Escuela de Metalurgia y Materiales de la Universidad de Birmingham, donde el grupo de él es Structural Alloys for Fusion Technologies. Bueno, para irnos rápido, doctor, vamos a darle la palabra de una vez. Él es experto en fusión materiales para fusión nuclear, ¿no? Y vamos a darle la bienvenida. Doctor, es todo suyo, tiene 25 minutos y 5 para preguntas después.
Sí, muchas gracias, Felipe, por la introducción. Voy a dar la presentación en inglés por si hay gente que no habla español o castellano. Y también porque alguna de las...
Tenemos todo el público habla castellano. Puede ser.
Sí, también me es más fácil hablar en inglés porque hay algunos términos que son más sencillos en inglés o que estoy más acostumbrado desde que no estoy en España, ¿no? De donde procedo.
Adelante.
Bueno, que comparta la pantalla. ¿Me confirmas, Felipe, si podéis verla?
Sí, la podemos.
Well, welcome everyone, and thanks for the kind invitation one more year to be part of this EMDA meeting for undergraduate students. So today I would like to show you a little bit about the challenges that we are facing and what I think are the opportunities in testing structural materials for fusion tokamak technologies, and how those tests will help hopefully to qualify materials and components, engineering components to build tokamaks or another fusion reactor technologies to deliver fusion energy to the grid. So what I'm gonna do first is to give you a big background to fusion energy and fusion materials, and then I'm gonna show you a few examples from my own research group about what kind of tests we need or we have been carrying out in order to understand mechanistically the behavior of materials and linking that to properties and performance. So in very general terms, fusion energy is released when light nuclei fuse together, provided that the resultant nuclei has a mass number above 56, and that's opposed to nuclear fission when you have a uranium fuel and then it's bombarded by neutrons and uranium. Nuclei just breaks in two or a number of pieces and then releases energy. So in fusion, what we're dealing is with, for instance, deuterium and tritium. And those, just a second, those elements will react and then will form, will release helium, will release neutrons, and will release a significant amount of energy. However, in order for the deuterium and the tritium to come close enough and overcome the Coulomb barrier. We need to make them confined in a high density environment. And one way to do that is to design what's called a tokamak or a donut-like plant, where we have very high magnetic fields that allow us to confine those tritium and deuterium atoms or nuclei very close together, and then they react and then generate neutrons and helium. That's in this yellow area in this donut shape tokamak. Then the neutrons will come out of the plasma phase on the first wall, and then will give us the energy or the heat that we can use to actually, in a power conversion system, to generate or supply energy and electricity. The neutrons will also react in what is called the tritium breeding module with lithium-6, and it will generate tritium. And that's important because tritium is radioactive, it's not stable, so it's very difficult to find it on Earth. So we have to generate tritium on site as the plant is progressing. There's also a very key component of the plant, which is called the divertor here at the bottom, which is kind of the exhaust system of our reactor, where we get deuterium and tritium from the ashes or any impurities in the plasma, and then we separate them, and then we feed the deuterium and the tritium from the plasma and the one generated by the neutrons back into the plasma clean again. Now, this is a very extreme environment for materials, and you can imagine that this is going to be under very high temperatures, especially close to the plasma. So if you can see this plot on the bottom right, you can see the temperatures currently characteristic of the current generation 2 and 3 fission reactors or plants. Then there's a number of generation 4 fission reactors that should go higher in temperature and in what we call radiation damage to materials, characterized by a new unit called displacement per atom, or DPA. Now, fusion will combine extremely high temperatures, up to 1,000 degrees and potentially higher, together with unprecedented levels of radiation damage. And this is an area where it is completely unexplored. So we are trying actually to build and qualify materials for a plant without having the knowledge to actually do it, or the research facilities to actually test those materials before they go at industrial scale. Now, where are we up to with this? So for several decades, as part of a European initiative, we've been running in the UK what's called the JET. That JET tokamak has been decommissioned in the last 3-4 years, and now we are learning a lot about how to decommission power plants, fusion power plants, and learn about those materials. For instance, how much the plasma phasing component or tile retains tritium and how we can extract that. Now, as you're probably aware, there's been already for, I think, 2 or 3 decades, an initiative at the international level to build what's called the ITER reactor or plant, which at the moment I think is going to be around 2035-ish in the south of France, with the idea that will be a springboard to demo reactors and future power plants. Now, in the UK, we've gone also a parallel route where from JET we've upgraded our mast tokamak, and the upgrade has to do with the better design and efficiency of that divertor at the bottom. And now we are aiming, and we have funding to do that, to develop what's called a step reactor, which is very much more compact design for that reactor. Now, irrespective of which route we are going, we hope to deliver fusion energy to the grid by maybe 2040s, 2050s. And we don't know what will be the demand for energy and the energy mix worldwide at that time. So that's an uncertainty that we have to cope with. Now, fusion was a hobby for physicists for years when I started this, but it has gone in the last 5 to 10 years what we call engineering. So fusion has gone engineering. So we not just need to understand fusion materials and plasmas, but we actually need to go at an industrial scale and build our engineered power plants. This is just the number of fusion-focused industries or companies worldwide. And you can see at the beginning there was a small number of them. But in the last, let's say, 5 to 10 years, this has exploded. And you can see how much it has branched out. And at the moment, there's more than 40 fusion-focused only companies worldwide try to develop different designs of fusion power plants. And the design is not unique, so different companies have different designs and different requirements. Now, a couple of years ago, the International Fusion Industry Association asked each of those companies what will be the main challenges up to 2030 and what will be those challenges beyond 2030. And you can see the list of responses. But in both cases, up to 2030 and beyond 2030, what we're going to need are materials which are neutron resilient. So materials are going to be key to actually engineer and construct fusion power plants. Now, we realized some time ago, in 2005, by Steve Sinkel in Oak Ridge, that the design of a fusion power plant station is one of the greatest materials development challenges in history. And that is because those materials will be under extremely harsh environments that we don't have experience at the moment. There will be high temperatures, and you see that it can go up to 1,000 degrees, high levels of radiation, much higher than those in the current nuclear industry, high production rates of transmutation elements, which means that the chemistry of the material that you design may not be the one that the material will have at the end of the lifetime. And that has consequences for the performance of the material. And also high thermomechanical stresses, and depending where the material, the component is inside the power plant, also corrosive environments, for instance, liquid lithium or any other liquid coolants. Any material that we use must have a good manufacturability, so we are going industrial scale at the moment, so we really need to make sure that it's not a small lab scale size material that we are developing, and it has to be reproducible, so we have to make tons of those materials. Now, if that's not enough, we have some additional challenges compared to fission materials, and that is that we have the production of significant amount of helium, and helium, unfortunately, is not soluble in metallic materials. So it means that if you have helium inside the material, it will start to move around, diffuse, and it will agglomerate and form bubbles. And I will show you some bubbles in a minute. But that helium comes, as you've seen, from the deuterium-tritium fusion reactor in the reaction in the fuel. But also, when the neutrons go through a given material, for instance, a plasma phasing material, it has some reactions that will generate helium inside the material. And to make things even worse, we also have the production of high energy neutrons, which are 14.1 MeV from the deuterium-tritium reaction. In the nuclear industry at the moment, the energies for the neutrons is 1 or 2 MeV. So we are going 14 MeV, and we don't have at the moment the facility to test materials in those neutron fluxes and energies. And as we discussed, we have to scale things up. We cannot just make small amounts of material. We just have to make sure that everything we do at lab scale can be also done at industrial scale. And how do we qualify materials, systems, and components in fusion when we don't have enough data and where there is no fusion standards at the moment, although they are being developed both internationally, both Europe and beyond. Now, if we don't know how to, before that, back in 2021, the Fusion International Community for Materials started to look around and think about what materials we can use for different applications within the power plant. And they came up with this relatively long list. What is important to realize, it was up here, the TRL, which is the technology readiness level, which means that how far are we from actually using that at an industrial scale. So it's just a small amount of material we actually can extrapolate and be used. And if you can see, most of them are at TRL 3-4 at that time. If you check the recent UK fusion material roadmap that was released 2 months ago, you will realize that some of them had advanced a bit, but not a lot. So we still have a long way to go, I think. Now, if we don't know how to qualify materials for fusion, the easiest is to look at the fission industry because nuclear energy has been going on for decades and they have had to qualify materials. So one of the standards comes from the ASME, the American Institute for Standards and Materials. And if those ASME codes require that for any new material that has to be in a nuclear environment, nuclear fission environment, we have to assess before that 3 possible modes of failure of that material: normal operation, off normal, and thermal cycling. we need material properties appropriate to prevent, ideally, any failure in service. And we need to know the stability of the properties, not just when we design the material, not just at lab scale, but at industrial scale over time and temperature. Any given material, since it has to be produced at an industrial scale, needs at least 3 different heats of material, preferably within a range of compositions within a given quite strict specification. And that at industrial scale is already a challenge. Now, if you see the number of tests or requirements that are needed in nuclear fission, it starts from testing mechanical properties, from simple tensile testing to time-dependent mechanical properties like creep. Then it all goes into fatigue, creep, fatigue. Then you start to look at the interaction with the environment, corrosion, stress corrosion cracking, and then things about irradiation effects. So all this could take, if you are lucky, at least 15 years from the time that you think that, oh yeah, my material is very good at lab scale. Let's see how we can adopt that at an industrial scale for nuclear. Now we need to look at fabrication of materials, and since we need to make components, we have to join materials. So we need to look at the properties of the welds, which normally are worse than the base material. Stability of the properties with time, and limited extrapolation allowed means that is one material, one component needs to survive at least 5 years. We need creep data or mechanical data continuously for at least a year and a half. That's already a challenge to run those tests. We need to test and inspect components and the welds. We look at environmental radiation effects. And of course, we have to limit the cost if possible and develop at the same time the supply chain. So let's see how we can do this. So as you've seen, there's very high temperatures, especially in what's called the plasma phasing components. So the components in the reactor were going to be closer to the deuterium-tritium plasma. So for those, let's see what we can do. We look at the periodic table, and we need good thermal conductivity because otherwise, as you see, in lots of temperature, we need to extract the heat as well, and we need relatively high melting points. Now, if you look at the periodic table, there's a number of them that can be used. Now, fusion is in theory a green energy, so we cannot generate, in theory, active material. So which ones will not produce any radioactive isotopes? Then we reduce the number of them. Then if we look at availability, cost, and radiation performance, then the number reduces even further. Molybdenum was not in the final list because of activation, but it's a potential option as a small amounts. Now, if we look at the susceptibility for radiation damage, so the amount of DPAs per year, as a function of depth from the plasma phasing wall, so imagine the plasma is at 0 in the x-axis, and you see how much damage that material will undergo as a function of depth and year or time, then you can see that iron and chromium, which are components of steels, are relatively quite susceptible. Beryllium is less, but it's toxic. So we end up mainly with tungsten, which is also the highest melting point material in the element in the periodic table. Now, tungsten is the not the ideal candidate, but it's the one that is currently being developed for plasma phasing components. It's brittle, and the ductile to brittle transition temperature is between 250 and 350 degrees, depends on the microstructure and the processing, but it becomes even more brittle at higher temperatures when it's under radiation in service. Vanadium is relatively good because it offers low activation, so less waste in theory. But if you start to look at chromium and vanadium, they have a higher sputtering rate. So it means that some of those elements, if they are in the plasma phasing component, they may end up easily in the plasma and contaminate our deuterium-tritium plasma. So let's go for tungsten, and I'm going to show you just a few examples that we've been working on in the last few years on some of the tests or understanding, very basic, very fundamental, but with the idea that that goes into performance later on, of how tungsten or tungsten-based alloys behave in fusion-relevant conditions. So tungsten as a plasma phasing material, so the material facing the deuterium-tritium plasma in the reactor will be under thermal loads, both steady-state heat loads and transients, plasma exposures and neutrons from the reaction, and all those things is a cocktail that can generate a number of problems or challenges for tungsten. from recrystallization, failure of joints, cracks, melts, dot formation, sputtering of tungsten, hydrogen retention, deuterium and tritium as isotopes, and helium-induced morphology, and I will show you a few examples of this in a second. And neutrons, they have extremely high energies. They can cause lattice defects in the material, so they can displace atoms from your atomic positions in your lattice, and they can generate other elements which are not desirable by nuclear reactions. So if you start to look at this, then if you start with tungsten, and we look at transmutation reaction now, over time in the reactor, it will start to generate rhenium as osmio, and instead of having a pure tungsten tile or component, then you start to have tungsten rhenium osmium. Now you may think, why is this important? If you look at the phase diagram, if you start with the alpha tungsten phase, as you start to form more rhenium and osmium, you go into the alpha plus sigma phase. And that sigma phase is brittle, so it will become more brittle over time. So one way to potentially retard or delay this process is to start with something different. Start with tantalum, and as tantalum goes down, it forms tungsten, and tungsten will form osmium and rhenium, but that process is delayed over as compared to pure tungsten. So what we've done in the group is to try to dope tungsten with a little bit of tantalum and see if that improves the performance of tungsten or not. Now, we're going to have helium, and we're going to have different, especially helium with different energies. So it's going to become helium from the plasma at electron volts or kiloelectron volts. Are going to form also helium inside the material as well in the bulk, not at the surface, but inside the material. If we look at first as the helium with low energies that comes from the plasma, depending on the temperature and flux and fluence, then we can form very close to the surface, a few nanometers, what's called nanobubbles. And if it is a relatively high temperature or higher, then we call these fast structures and large voids. And as you can imagine, this is not good for the integrity of those components. So as an example, what we did is to put tungsten and tungsten tantalum alloys at the differ facility, where we irradiate them or expose them to low energy plasmas at 400 degrees, and I'm going to show you what we found out as a behavior. So you can look at the surface with laser scanning microscopy or simply optical microscopy, and this is what you see for tungsten or tungsten with a little bit of tantalum. You see quite some roughness, and then you see all those black dots, and which are blisters and protrusions, right? It's ablations as well, that because some of the material at the end ends up being released from the surface. That surface roughness depends on how much tantalum we put in, so that's good news. And that behavior seems to correlate with the number of blisters, but especially the ablations. So what we think happens is that helium, if you look at number 1 sketch, helium goes a few nanometers on the surface of tungsten, diffuses, agglomerates, forms small clusters, then small bubbles. Those bubbles start to agglomerate and they form blisters, and at some point the blisters just have so much local strain that they actually eject material and causes ablations on the surface. So what we think is that by putting a little bit of tantalum, it delays the start of the process, the helium diffusivity, before they form the small bubbles and the blisters. Now, if we look at higher energies of helium, or if we look at helium generated inside the material, then we can have helium bubbles as well, not just very close to the surface, but also in the bulk of the component. One way to look at this or to understand the process is what we did, which is to do transmission electron microscopy in situ in real time while we are exposing the material to, in this case, helium ions that we are implanting. And we did this at 800 degrees, and we wanted to understand is how those helium bubbles form in those materials. You have to think that for transmission electron microscopy, what's called the TM sample or lamella is very thin. It's around 100 nanometers in the area that you are analyzing. But you can see as you increase the dPA, you can increase the damage or the fluence, how you start to form all these white dots, which are all these helium bubbles, and they start to accumulate and grow. And you can look at the very earliest stages of that formation. We can do the same if you do tungsten tantalum, and then you can compare at the end of the process what's the situation, and then you can see all these big bubbles. Now, was done by one of my PhD students, that he looked at characterizing the size of the bubbles and how many of them you find. And then you see that at the end of the process, at 1 dPa, you reach the same level, but it seems that the size is lower when you put a little bit of tantalum, but also delays the start of the bubble formation. So it doesn't solve the problem, but it delays a little bit the problem. We also look at what's called, we use proton beams not to insert hydrogen, but to actually as a surrogate of neutron damage, with the idea is that we put enough energy in the material to actually cause radiation damage and displacement of those atoms in your microstructure. But the protons are outside the area that we are analyzing. Now, those black dots that you see here as a function of dPa or radiation damage are not bubbles in this case. They're called dislocation loops, which are lattice defects that they can move, they can evolve, and they create this rafting. And that rafting of those structures, those elongated structures, has also been observed in tungsten with neutrons. So it's a good surrogate to use protons for neutron damage. If we put a little bit of tantalum, you see similar features, but you don't see that those elongated structures at higher fluences or damage. Well, without going into all the details, we can compare if you do it in situ with medium energies or ex situ with high energies to avoid surface effects, and then you can count the number density as a function of dPa and the average loop size, and then you can see that one of the dimensions doesn't grow, so you don't form those elongated structures that you form in tungsten. Now, something else that we are also interested in fusion is not just to isolate different parameters or different conditions, but to actually look at what's called synergistic effects. So you have more than one thing going on in parallel and affecting your material. And as we've seen, we have helium generated from the transmutation reactions, helium from the fusion reaction, but you also have lattice damage, and we also have tritium, which is, as you will see, radioactive and can be retained in the material, and then it generates waste at the end and problems how to decommission those power plants. So what we've done in that case was another PhD student looking at tungsten molybdenum alloys, not tantalum, but another element, to see if that helps or not. So what we did is to irradiate those materials with helium at 300 degrees up to a damage level of 0.5 dPa. And once the material has some of those bubbles and damage, then we expose those materials to a deuterium-tritium gas at 400 for 5 hours. And we wanted to see if just by having helium and lattice damage will affect or not, or make things worse instead of retaining the tritium, which is something we don't want to retain because we need it for the fuel and because it's going to cause activation problems for decommissioning. Now, since the tritium is radioactive, we can measure it with image plates and with what's called beaks, as I will show you in a minute. These are the material or microstructures that we made. Those materials are made by powder metallurgy, and then afterwards you hot roll the material at high temperatures. We can simulate the damage profile and the helium concentration and look at how it evolves or changes with the amount of molybdenum. What is more impressive, I think, well, first of all, the tritium decays into helium electrons and what's called an antineutrino. That tritium has a half-life around 12 years. So we don't want to lose tritium, and we don't want tritium in any reactor component that later is going to cause radioactive waste. Now, those electrons have a given energy or energy distribution that interact with the material and cause what's called Bremsstrahlung radiation and characteristic X-rays. The maximum X-ray escape depth corresponds to the depth of damage induced by helium irradiation. So in other words, we can use this to actually understand where the tritium is in the microstructure. The first thing you can do is put an image plate And then you can see for those materials and the ones which were not pre-implanted with helium and the difference in the activity, radioactivity that you see. So if you have helium and damage, it makes things worse or it retains more tritium as compared as isolating the effects independently. And then we can also do measure the energy profile and simulate that. You see a number of peaks. Those are from tungsten of molybdenum. You also see argon, and that's because we did the experiment or the spectroscopy in an argon environment. So the X-ray that escape from the material before reaching the detector also go through some argon, but it's not from the material itself.
Profesor,
We spent
2 minutos, profesor.
see, nearly done. So you can look at the spectrum, and then from there, after some simulations, that you can get the tritium profile with or without pre-implantation. You can compare with the damage or the helium profiles. So tritium trapping is increased by the damage. So if you have helium implantation prior to that, then you retain more tritium. That's bad news. Tritium retention reduces with a higher amount of molybdenum content, so you can tweak the chemistry of the material and minimize or reduce the amount of tritium retained. But the maximum depth at which the tritium is trapped increases when you increase the amount of that alloying element. Now, this is just to show you a cross-section of what I showed you before of the tokamak, where the plasma will be in the middle, just to show you that different components in the plasma-facing materials, or in the first wall, will have different conditions. You still will have tungsten and copper core zirconium as zinc, but the heat flux or the coolant, they are very specific. So we need to understand the local environments even within the first wall of the tokamak. Very quickly, there's quite some work being done at the moment to try to optimize the interfaces of the material, create multi-layer materials to actually reduce the damage or the helium formation, both with simulations and with experiments. And we are also exploring the idea of near net-shaped components by additive manufacture. So ideally, we will not need much more machining or shaping after that additive manufacture. Now, if you look at, you search up research in Wikipedia, you will find this solution or this definition. So it's the creative, systematic work undertaken to increase the amount of knowledge, but we need to use that knowledge to devise new applications. And I'm giving you an example of those. So we need to understand materials for fusion to actually go into future power plant development and engineering. So if you are an early career researcher or engineer and you want to look for a challenge, this is one of them. This is the interior of jet. You can see all the tiles, but this is extremely demanding conditions, and all the scientific and engineering problems needs to be tackled in the next years. This is not just an academic hobby. There's already quite a number of small fusion plants or experimental devices worldwide, not just tokamaks, but also inertial laser confinement, stellators, and so on. So this is something really happening, going into industry, but in all cases, we have the same challenges in terms of materials. And that's the end of it. I hope I convince you this is challenging enough for anyone who wants to undertake a materials engineering challenge in the future. And I'm going to stop my presentation, I think. I'm happy to answer any questions.
El Instituto Politécnico Nacional en la Escuela Superior de Física o Matemáticas. La práctica que nos va a dar de hoy es espectrometría, prospección de Rutherford y canalización para caracterización de películas delgadas, estructuras y materiales porosos. El doctor Osvaldo de Melo es un físico distinguido en el área de materiales semiconductores, películas delgadas y nanotecnología. Nacido en La Habana, Cuba, en 1957. Se trabajó principalmente en monocristales de compuestos 2,6, entre fluoruros principalmente. Tiene más de 40 años de experiencia en la Universidad de La Habana, en la Universidad Autónoma de Madrid, en la Universidad Federal de Minas Gerais y en el Instituto Politécnico Nacional también. Doctor Osvaldo, le agradecemos muchísimo su tiempo, es un honor tenerlo aquí con nosotros. Tenemos un público de ingenieros en nanotecnología y de ingenieros en mecánica, ingeniería mecánica, entonces es todo suyo el público, tiene usted 25 minutos. Gracias.
Bueno, ¿me escuchan bien?
Sí, doctor, lo escuchamos y se ve bien la presentación.
Bueno, pues, ¿estaba viendo aquí? Bueno, muchas gracias por la presentación y muchas gracias por la invitación a participar en este congreso, EMDA, en la edición número 5. Y yo, bueno, voy a hablar de un tema que me parece interesante para este auditorio. Es una técnica que se denomina espectrometría de retrodispersión de Rutherford. Es una técnica cuyos principios básicos son bastante sencillos, digamos, basados prácticamente en la física elemental, pero que es muy útil para muchas caracterizaciones sobre diferentes materiales, ¿no? En particular, yo voy a hablar después de después de la introducción y voy a decir los elementos básicos, los parámetros básicos de la técnica, incluyendo el Rutherford Backscattering y la canalización. Y después voy a dar ejemplos de la aplicación de esta espectrometría para la caracterización de películas delgadas y heteroestructuras de materiales porosos y también de materiales con composición gradual y estudio de transformaciones de fase. ¿Ya? Como ustedes ven, hay un amplio rango. Yo voy primero, bueno, voy a recordar primero los experimentos de Rutherford. Rutherford es uno de los científicos más destacados de la historia de la ciencia. Él hizo muchas cosas, pero en lo que nos ocupa, él hizo experimentos para ver cómo se dispersaban las partículas alfa en el material. Con sus dos estudiantes estrellas, Heger y Marsden, ellos bombardeaban una lámina de oro muy fina con iones con partículas alfa y estudiaban cómo se dispersaban las partículas alfa. Ellos esperaban que se dispersaran muy poquito, que cambiaran su dirección solo muy poco, de acuerdo con el modelo del átomo que en aquel momento existía, que era el modelo del átomo de Thomson, que suponía que el átomo entero era una esfera de carga positiva con los electrones adentro como las pasas en un pudín. Algo es una esfera tan grande positiva, pues no podía tener un campo eléctrico tan grande en la superficie y no debía hacer una gran cambio en la dirección de las partículas alfa. Sin embargo, ellos empezaron a ver que había algunas partículas alfa, muy pocas, pero había algunas que retrocedían, casi daban la vuelta en U. Con la lámina, al llegar a la lámina de oro. Y creo que dicen que Rutherford le dijo a los estudiantes que tenían que repetir y que repetir y repetir el experimento porque esto no era posible, hasta que se convencieron de que eso era lo que pasaba. Y entonces dicen que Rutherford dijo que algo así como que es como si disparara balas sobre una hoja de papel y me rebotaran hacia atrás. Y esto concluyó con una propuesta de la estructura atómica en la cual la carga positiva no ocupaba todo el átomo, ni mucho menos, sino que estaba concentrada en una porción muy pequeña del átomo, lo cual hacía que tuviera un campo eléctrico muy grande en la superficie y los electrones giraban alrededor. Este fue el modelo, digamos, planetario que fue el primer modelo del átomo que consideraba la existencia de un núcleo atómico. Y él le dieron el premio Nobel de Química en 1908 a Rutherford. Bueno, voy a explicar las bases de esta espectrometría. Eh, uno tiene una partícula pequeña, de masa pequeña, que es, por ejemplo, la partícula alfa, aunque también se pueden usar protones o se puede usar átomos de litio. Y tiene un átomo que está en el material que vamos a estudiar, que en general tiene una masa más grande. Bueno, lo que ocurre es esto: la partícula incide con su energía cinética, rebota en el átomo y el átomo recula con una energía E2 y un ángulo phi. Las ecuaciones que rigen esto son las ecuaciones de conservación del momento lineal y de la energía cinética, como ustedes estudiaron en los primeros años de la ingeniería o de la física. Y si de estas ecuaciones nosotros eliminamos el ángulo phi y la energía E2, o sea, la velocidad V2, pues obtenemos esta relación, que es la relación entre la energía con que rebota la partícula y la energía con que llegó. Eso se llama factor cinemático. Y fíjense que este factor cinemático nos permite lo siguiente. Aquí en esta expresión, E1, esto que he señalado con flechas son los datos que yo poseo de mi experimento. O sea, la masa de la partícula incidente, el ángulo con que hago incidir la partícula, son los parámetros que yo pongo en el experimento. Y la energía inicial de la partícula, la energía con que incide. Después yo tengo la energía con que se rebota la partícula, con que se dispersa, que es lo que se mide en el experimento. Y por medio de esta ecuación se puede calcular, la incógnita en esta ecuación sería la masa del átomo con que chocó. Como ustedes se dan cuenta, entonces, midiendo la energía de la partícula, yo puedo determinar la masa del átomo con que chocó la partícula y por tanto hacer análisis químico. La masa, al saber la masa, ya sé cuál es el átomo con el cual chocó. O sea, la posición en energía en un espectro de la partícula que dispersada nos indica el valor de la masa con lo que tropezó. ¿Por qué se usa retrodispersión? Porque retrodispersión quiere decir que este ángulo es 180 grados. ¿Por qué se usa retrodispersión? Bueno, se usa retrodispersión porque se usa retrodispersión porque es la manera, si ustedes, no lo voy a hacer aquí detalladamente, pero si ustedes buscan la manera de tener un delta M lo más grande posible para un dado delta M, o sea, para tener resolución en el espectro, pues lo óptimo es tener un ángulo de 180 grados. En la práctica no se usa 180 grados, sino más o menos 170 o algo así. Bueno, el otro aspecto interesante es el siguiente, o sea, para el análisis cuantitativo de un espectro no nos hace falta saber solo la posición de los picos, no solo determinar la masa, nos hace falta también saber las intensidades que van a tener los picos. Y eso está relacionado con la sección eficaz de dispersión. Esto que está aquí es la sección eficaz por unidad de ángulo sólido. Y como ustedes ven, se ve que depende, es lineal, bueno, depende de los mismos parámetros que dependía la posición, pero también depende de los números atómicos, es proporcional al número atómico tanto de la partícula incidente como del átomo que chocó. Esto hace bastante sencillo calcular, hacer la simulación de los espectros o distinguir entre las intensidades de dos elementos diferentes, porque es proporcional al número atómico. O sea, la posición más bien, ¿sí? ¿Sí? Ok. ¿Me escuchan bien?
Se escucha perfecto, sí.
Ok. Bueno, ¿sí? Bueno, les decía que bueno, entonces, sabiendo esta sección eficaz, se puede saber la cantidad de partículas dispersadas para un dado ángulo y energía de la partícula. O sea, la cantidad, el número, bueno, evidentemente la cantidad de partículas que se dispersan es proporcional a la cantidad de partículas que uno lanza, ¿no? Al número de iones incidentes, que vamos a llamarle Q, porque es la carga, generalmente se da como la carga que estoy enviando, que las partículas son iones, pues se da dependerá también de la cantidad de partículas, de cantidad de átomos que tenga adelante el haz de partículas alfa o de las partículas incidentes. O sea, mientras más átomos tenga adelante, pues mayor cantidad de partículas se dispersarán, lógicamente. Y el número de átomos que tiene delante, bueno, será la concentración, la densidad de átomos por el espesor. Y O sea, mientras mayor espesor tenga la muestra, mayor átomos va a tener delante las de partículas. Si la concentración es más grande, también mayor cantidad de átomos habrá en el trayecto de la partícula. Y claro, también depende del ángulo sólido del detector, ¿no? Del tamaño del detector con respecto, mientras más grande sea el detector, pues más partículas va a detectar. Entonces, con esto, es bueno señalar que en esta expresión, Rutherford backscattering no puede discernir entre N y T, entre la concentración de partículas y T. Es lo único lo único que sabe, digamos, entre comillas, es que la cantidad de átomos que tiene delante el haz. La cantidad de átomos que tiene delante el haz. No puede diferenciar si esta cantidad de átomos es grande porque la concentración es mucha, porque el espesor es grande. De hecho, para mostrar esto un poco más claramente, si yo tengo una muestra, digamos que este es el área, una muestra, digamos, cilíndrica con un área de 1 centímetro cuadrado, pues si yo tengo esta muestra que digamos con una densidad determinada, constante, y es una muestra compacta, produce un espectro RBS. Si yo tengo esta otra muestra, que es una muestra que tiene espacio poroso, espacio vacío dentro, el espectro RBS será exactamente el mismo, porque solo interesa eh, la cantidad de moléculas o la cantidad de átomos que tiene delante las. Si esas moléculas están muy agrupadas y ocupan un espesor pequeño, o si esas moléculas están menos concentradas y ocupan un espesor más grande, eso no importa, da lo mismo. Por eso, si yo quiero saber el espesor físico, de la muestra, yo tengo que saber cuál es la concentración de partículas para entonces dividir el número, este n por t entre eso para saber el espesor físico. Bueno, el otro punto interesante en esta espectrometría es la pérdida de energía. Por ejemplo, si la colisión entre la partícula incidente y el átomo se produce en la superficie, bueno, pues uno sabe con qué energía se rebotará la partícula conociendo el factor cinemático. Pero si la colisión se produce en el interior de la muestra, pues la partícula va a perder energía en el trayecto que va de la superficie hasta el átomo donde chocó, y después otra vez desde que rebotó en el átomo hasta que regresó a la superficie va a perder energía. Por tanto, va a haber una pérdida de energía en los trayectos por dentro de la película o del material que se está midiendo. Esa pérdida de energía depende del material, claro, y de la energía, del tipo de partícula y la densidad de la muestra y de la composición de la muestra. Depende de esas cosas, y generalmente está tabulado, se hacen mediciones empíricamente de estos parámetros, y eso está tabulado en los programas o en las tablas que se usan para hacer la simulación. A grosso modo, una partícula alfa, un valor que de 2 megaelectronvoltios, pues pierde 100 o 800 electronvoltios en cada nanómetro de camino. Entonces, evidentemente, el delta E, o sea, la pérdida de energía, será proporcional a la cantidad de partículas que se encuentre el haz en su camino, y el factor de proporcionalidad, que depende, como les decía, de la composición, del tipo de partículas, así, es lo que se conoce como poder de frenado. Poder de frenado. Y se da en estas unidades, electrón-volt, que es la unidad de energía, entre la cantidad de átomos por centímetro cuadrado, que es la unidad natural de espesor del RBS. Bueno, quiero hablar un momento de las desviaciones del RBS. Para bajas energías, pues, ¿qué pasa? Que los átomos, si la energía no es de la partícula incidente, no es muy grande, pues los electrones pueden apantallar la carga del núcleo, y entonces esto que hemos visto aquí, esta deducción que hemos visto, no funciona bien, porque la partícula no llega a chocar. Fíjense que nosotros lo que hemos asumido es que la partícula choca con el núcleo como dos bolas de billar. Si la energía es baja, esto no llega a ocurrir. Hay un rango de energía que estamos en el régimen RBS, donde se produce este choque tipo bolas de billar, Y entonces para altas energías, entonces lo que ocurre es que para alta energía la partícula se interacciona fuertemente con el núcleo, aparecen fuerzas nucleares y entonces aparecen reacciones nucleares. O sea, digamos que la partícula es absorbida por el núcleo se vuelve inestable y emite la misma partícula o emite otra después con una energía determinada. Hay veces que esto entonces no funciona el algoritmo que hemos hecho. Hay veces que esto es necesario cuando tenemos átomos que dispersan muy poco por RBS, se utilizan estas reacciones. Bueno, para altas energías ocurre eso. O sea que siempre tenemos que buscar un rango del RBS que la energía, si queremos tener RBS, un rango intermedio de energía, siempre están alrededor de los megaelectronvoltios, ¿no? Bueno, yo les voy entonces, basado en lo que acabo de decir, les voy a mostrar con esta ilustración que voy a poner ahora, más o menos cómo funciona, cómo son los espectros, más o menos cómo son los espectros. Yo tengo aquí tengo este material que está compuesto por una película, que es una película compuesta por un compuesto de átomos amarillos y azules, donde los amarillos serían átomos de mayor masa y los azules átomos de menor masa, y está depositada sobre un sustrato que tiene átomos azules nada más, pero con una concentración más grande que en la superficie. Esto pudiera ser, por ejemplo, un sustrato de silicio y una película de silicio germanio, para ponernos así, ¿no? Para que no sea algo demasiado abstracto. Podría ser algo así. Entonces, bueno, yo tengo, se hace incidir una partícula alfa y se mide la energía de esa partícula alfa y conociendo, vamos a suponer que esa partícula alfa interactuó con un átomo amarillo de los masa grande, pues dará lugar a una partícula rebotada con una energía que en este eje de aquí, esto sería el espectro, y este eje de aquí sería el eje de las energías, con una energía determinada, relativamente alta, porque como la masa es alta, el coeficiente utilizando el coeficiente cinemático, pues tendremos una energía también bastante alta. Ahora, vamos a suponer que tenemos una partícula alfa que en vez de rebotar en la superficie, rebota en una partícula amarilla de masa grande, pero en el interior. Pues esta partícula, durante este trayecto perdió energía, durante este trayecto también, por lo tanto, ella va a aparecer, la partícula que se dispersó en este átomo va a aparecer a una energía menor. Y en el intermedio van a estar todas las otras partículas y por esa razón lo que se espera para el espectro correspondiente a las partículas amarillas, a los átomos amarillos, sería una meseta de este tipo. De hecho, los espectros RBS están caracterizados por mesetas. Evidentemente, lo que acabo de explicar, el ancho de esta meseta va a depender del espesor de la película. Si la película es muy grande, pues este ancho va a ser más grande porque la pérdida de energía de las que entran hasta el final de la película va a ser mayor, ¿no? Si la película es muy estrecha, pues esta meseta va a ser más estrecha. Pero esta es la forma en general que tiene. Entonces, vamos a analizar las partículas azules. Si viene una partícula alfa, la partícula azul, pues ahora dará también una partícula dispersada con una energía menor, porque la masa de esta partícula es menor. La que rebota al final de la película va a producir igual la meseta de las partículas azules. Claro, como después los átomos de helio siguen llegando para aquí, al sustrato, y como el sustrato es muy grande, pues en general esta sería una meseta que prácticamente no termina, sería una meseta muy grande. Fíjense que esta meseta, a pesar de que es el mismo tipo de átomo del que está en la película, es azul también, pero como aquí los átomos tienen mayor concentración, pues entonces la intensidad es mayor por lo que vimos en la ecuación de la sección eficaz de dispersión. Esto es más o menos la idea. El otro aspecto que quiero hablarles interesante es el problema de la rugosidad. Si una muestra es rugosa, ¿cómo afecta eso el espectro RBS? Bueno, si una muestra es rugosa, fíjense que lo que tenemos, la superficie es siempre la superficie. De hecho, yo pudiera pensar, si yo quiero ponerme distancia de la superficie, lo que tendría era algo así. Una superficie así y las muestras tienen diferentes anchos. Es como si una muestra rugosa estuviera compuesta por muestras columnares que tienen diferente espesor. Esto ¿qué es lo que hace? Que el efecto de la rugosidad se ve en la parte de baja energía. La parte de la superficie, o sea, el borde de alta energía de la meseta queda en el mismo lugar. Lo que varía es, como en cada caso va a haber un espesor diferente, lo que varía es los espesores. Cuando todos esos espesores se superponen, lo que me queda es una meseta que tiene una cola a baja energía con la cual se puede determinar la rugosidad de la muestra. ¿Qué les quiero decir con esto? Que entonces con RBS uno puede determinar el tipo de átomos que hay en la muestra, el espesor, si tienes una película, el espesor de la película, y se puede determinar también la rugosidad de la película. El otro aspecto interesante, que ya no es una espectrometría, sino es un efecto geométrico, es lo que se conoce como canalización. Si ustedes se fijan, yo pinté aquí el gráfico del material, lo pinté un poco inclinado. No fue que no cometí un error, lo hice a propósito, lo voy a explicar por qué. Si yo hago, si esto es, si yo hago que si la muestra es monocristalina, como por ejemplo en este caso, una muestra monocristalina puede tener como canales. Esos canales serían lugares donde donde las partículas alfa pueden pasar de largo y no rebotar con nadie. Por lo tanto, si una muestra está desorientada, aunque sea monocristalina, pues generalmente las partículas alfa no van a pasar por estos canales y vamos a ver el espectro normal que he descrito anteriormente. Pero si una muestra está orientada perfectamente con respecto a las de partículas, pues puede ocurrir que las de partículas pase por aquí hasta el fondo y no se obtenga prácticamente partículas dispersadas. Eso se observa de la manera siguiente. Esto es una película de zinc teluro sobre el celuro de galio, que son dos semiconductores bastante conocidos. Y aquí se ve el espectro que se vería de Rutherford Backscattering en el caso de que la estructura esté desorientada, y en el caso en que esté orientada, que esté canalizada, pues se ve cómo disminuye la intensidad, porque ahora las partículas, en vez de rebotar, pasan a lo largo por los túneles del monocristal. Bueno, aquí les pongo en esta lámina, también está en el artículo que mandé para publicación, una serie de unas referencias por este SIMRA, Simulation Nuclear Reaction Analysis, es un software que permite simular los espectros. Es un software muy bueno, uno se siente como si estuviera haciendo un jueguito. Uno va poniendo el espesor que uno cree que tiene, los elementos que tiene y se va reproduciendo el espectro. Lo que voy a hacer a continuación en los ejemplos que pongo es exactamente los espectros las simulaciones han sido hechas con este programa de Mayer. Bueno, el primer caso que voy a poner es el caso del bismuto teluro. El caso del bismuto teluro es el bismuto. ¿Qué tiempo me queda, por favor?
Ya tenemos 5 minutos, doctor.
Bien, el caso del bismuto teluro es un material que tiene, teniendo los mismos elementos, pues tiene diferentes composiciones. Y aquí tenemos, por ejemplo, el bismuto 2 teluro 3, el bismuto teluro y el bismuto 4 teluro 3 con diferentes composiciones. Estos son los espectros de RBS y la simulación correspondiente. Fíjense la diferencia de altura entre los picos de bismuto y teluro debido a la diferente composición. La simulación permite calcular la composición. Quiero aclarar que no hace falta estándares. Comparado con otras técnicas que hace falta para saber la composición, tener un estándar para comparar, aquí no. Aquí con esta simulación sencilla se puede saber la composición sin utilizar ningún estándar. Por otra parte, le quiero mostrar el resultado de canalización de una muestra en este caso, canalización planar. El sustrato, la muestra se hizo girar en los ángulos phi y teta y se fueron midiendo espectros de Rutherford Backscattering en cada posición, en cada combinación de phi y teta. Y aquí se ve que se obtuvo como para determinadas posiciones la intensidad del espectro, de los espectros disminuye. Y disminuyen en la misma posición para el sustrato y para la película, que el sustrato es un sustrato de silicio. Eso indica no solo que tenemos un monocristal, sino que tenemos una orientación cristalina la misma en la película que en el sustrato. O sea, eso se llama crecimiento epitaxial. Bueno, esto es otro caso del el indio galio nitrógeno, que es un material bastante importante en relación con, es un semiconductor que se llama de gap ancho. Esto es una muestra de nitruro de galio, donde se puede determinar el espesor 1.1 micra en este caso, a partir del ancho de la meseta del galio. Y aquí tenemos los aleaciones con diferentes composiciones. Fíjense cómo la altura de de la meseta del indio y del galio, la relación entre ellas cambia en función de la composición. El caso, cuando aumentamos el indio, ocurren una serie de defectos que aumentan la rugosidad de la película, como se ve aquí. Bueno, quiero mostrarles el caso de la porosidad. El silicio poroso, ustedes saben, es un material que se puede hacer, que se hace de forma que es esencialmente silicio con muchos huecos. Vamos, eso es la idea. Si uno mide, por ejemplo, y una cosa que se puede hacer es infiltrarlo para obtener determinadas propiedades, por ejemplo, para obtener nanocristales en el interior, para lo que se puede filtrar. Utilizando determinadas técnicas se puede infiltrar y es bueno chequear si se infiltró o no. Yo quiero señalar, por ejemplo, si uno hace una medición de difracción de rayos X, pues puede determinar que ha puesto sinteluro en los poros, en algún lugar, pero no sabe si se infiltró o no. Como el RBS da una información que no solo depende de la sustancia que tengamos, de los elementos que tengamos, sino depende de la profundidad que estén de la superficie, pues entonces con los espectros RBS sí se puede saber si el sinteluro se introdujo o si no. Aquí estos son los espectros. Fíjense el ancho de las mesetas del zinc y del teluro, como, que son bastante anchas, como si digamos que están bastante extendidos, ¿no? Y aquí se ve los perfiles de composición. Ajustando, simulando este proceso, se pueden hacer perfiles de composición y se ve cómo, por ejemplo, el sinteluro, este es el silicio, este es el silicio, y aquí prácticamente no hay silicio, y este es el sinteluro, fíjate que sí, efectivamente está infiltrado a lo largo de toda la película. Bueno, este es otro caso, estos son los casos, las heteroestructuras que le quería mostrar. Esto es una heteroestructura que quiere decir que tiene una película de sinteluro, una de cambio de teluro, otra de sinteluro. Ya casi estoy, ¿no? En el tiempo.
Ya,
Y,
prácticamente ya.
y aquí tienen el espectro. Fíjense que aquí se ve como el teluro, que es más ancho, porque está aquí y está aquí, pero que el teluro tiene como dos regiones, una región externa y otra interna, y el cambio se ve metido dentro aunque el cambio tiene menor masa que el teluro, pero como la película de cambio es más fina, el ancho es más pequeño. Y aquí se ve el zinc que está superpuesto con el sustrato. Pero de esta manera se puede encontrar cuál es el perfil de esta heteroestructura. Esta es otra heteroestructura un poco más compleja donde tenemos barras, rods de nitruro de galio que están embebidos en galio, aluminio, nitrógeno. Esto es un sistema que puede generar, por ejemplo, pozos cuánticos o alambres cuánticos. En estas regiones donde hay confinamiento, pues aquí se ve cómo el espectro de RBS permite ver el aluminio, permite ver el galio en la película exterior, en esta de aquí, y permite ver el galio en esta parte de aquí, que es más grande porque aquí tenemos el galio mezclado con el aluminio, pero además tenemos el galio. Y como promedio tenemos más galio en esta región, por tanto la intensidad sube. Esto permite hacer un estimado de los espesores y incluso del área que está descubierta aquí. Bueno, el otro es el caso de las composiciones graduales. Se pueden hacer composiciones graduales para mucho, pues en este caso era para estudio de celdas solares y también, por ejemplo, uno va aumentando, uno va creciendo películas alternadas de telururo de cadmio y telururo de zinc y producto de la difusión, estas películas terminan por generar una región donde la composición es variable. Se hace un tratamiento térmico posterior, pues entonces se obtiene una estructura gradual, ¿no? De composición gradual a partir de la distancia de interfase. Pues esto también se puede determinar. Aquí tienen, este es el espectro RBS y simulando este espectro se puede determinar. Esto es otra técnica que es SIMS, Secondary Ion Mass Spectroscopy, y esta es la simulación por RBS de la composición de ese perfil. Bueno, aquí por último les voy a mostrar otro caso, que es el caso de la transformación de fase del óxido de molibdeno 2 al óxido de molibdeno 3, donde se puede, con los espectros, se puede determinar la diferencia entre uno y otro y se puede incluso encontrar la composición, en el caso de MO2, menos oxígeno con respecto al molibdeno, en el caso del MO3, más oxígeno con respecto al molibdeno. En resumen, RBS es una técnica que es verdad que requiere una instalación grande, requiere de un acelerador de partículas, pero aún así no es una instalación demasiado complicada. Aquí en México hay sistemas de aceleradores de partículas que permiten hacer RBS y en otros países también hay bastantes sistemas de este tipo que generalmente dan capacidad para poder hacer mediciones en estos lugares. Y bueno, en resumen, se pueden identificar los elementos químicos, se puede dar la composición utilizando la relación de las alturas de las mesetas, se puede determinar el espesor de las películas por el ancho de las mesetas, se puede caracterizar la rugosidad mediante la simulación de la cola de absorción y se pueden determinar expresiones y composiciones en heteroestructuras. Se puede complementar el RBS con reacciones nucleares. En el caso de los elementos ligeros que no tienen un RBS eficiente, pues pueden hacerse reacciones químicas. Y por otra parte se puede hacer canalización para verificar el carácter epitaxial o estudiar la presencia de átomos intersticiales y ese tipo de cosas. Bueno, quiero agradecer a mis estudiantes que han participado en estos trabajos en los últimos, ya desde hace algunos años. Y las mediciones de RBS se hicieron en la Universidad Autónoma de Madrid y en la Universidad Federal de Río Grande do Sul en Brasil. Y las muestras preparadas en parte en mi grupo y en parte en colaboración con otros colegas del CIMBESTAB. Bueno, muchas gracias por escucharme y estoy atento a las preguntas que pueda haber.